hope all of you are doing well. Today we are going to discuss a very interesting problem going by the name Fermat's extra large theorem. So first we'll take a look at the problem statement and then we'll figure out an optimized way to solve this problem. Alright, so the problem statement says that the Fermat's little theorem states that if p is a prime number, then for any integer a, the number a to the power p minus a is going to be an integral multiple of p. What does that basically means over here is, if I consider a number a which is any integer 5 and p as a prime number 2, then a to the power p minus a, which is nothing but 5 to the power 2 minus 5, 25 minus 5 is 20. Now this number is always going to be a integral multiple of p, which is true as well, as you can see over here. Now with this, a new theorem is defined which is called as the Fermat's extra large theorem, which states that the total number of unordered pairs, okay, so you form a pair by taking a integer value two integer values at the indexes I and j, right, from a particular array A which has a size n, such that we are also going to be given three integers s, p and m, right, and the following equation holds, that is ai plus aj, that means the elements at the indexes I and j when added and taken the modulo with m is going to give s, and the same elements at those indexes when multiplied and then taken a modulo with m are going to give the element p. Okay, now remember I and j will be less than equal to n, so that means here we are going to follow 1 based indexing and not 0 based indexing. Okay, now we have to apply the Fermat's extra large theorem and basically print the total number of unordered pairs which actually follows the theorem. Okay, so let's take a look at the properties. So it says that you will take two indexes I and j, and when you basically add the elements at those indexes, take a modulo of m, you will get s. Similarly, for those same elements only, here when you take again their modulo m, but this time the elements are multiplied, you will get p. Okay, so this is what the two equations are going to be. Now here what you have to do is, you can see in the input that you will be given n, m, s and p, which is the first line of input, and then you will be given all the elements of the array, which are n integers basically, because n defines the size of the array. And in the output format you have to print the answer, and thereby you have also been given the constraints for the question. So you can see here that the elements given are 4, 2, 1, 0, which is 4, 2, 1, 0, which is n, m, s and p. So n is the size of the array, m is the modulo you take with, and s and p are the answers. And here the array elements given to you are 1, 2, 3 and 2. So these are the elements. Okay, and then you basically need to print the output. So output is 4. Okay, how is that? Because here you don't have to find the elements, right, or the elements of the pairs which are forming the or holding this equation. You simply have to find out the number of pairs which kind of satisfy this. So this is one important thing that you need to consider. You don't have to store the elements anywhere which satisfies the condition. Just you need to count the number of elements which basically satisfy this equation. You can see the value of n was 4, hence you got 4 elements of the array. So, and since we are following 1 based indexing, so this is first index, this is second index, this is third index, and this is fourth index. Okay, now with this, let's see how come the answer came out to be 4. Okay, so the first pair I can see that is satisfying this equation is basically at the index 1 and 2. How is that working? So if you consider the element at this index, that is 1 and 2, so this is 1 plus 2, adding ones, and 1 into 2, multiplying ones. Okay, now when taken the modulo of both with 2, which is m, Okay, here one time you should guess S, which is 1, and one time you should get P, which is 0, which is correct as well, right? 2 plus 1 is 3, modulo 2, remainder is 1. 2 into 1 is 2, so when you take in the modulo of it 2 only, you get the answer 0. So one of the pairs which are at these indexes and the corresponding elements are also this. Now I see that if this satisfies the answer, then for sure this will also satisfy the answer, because if this is a valid pair, then this will also be a valid pair, right? So hence you can conclude with this, that since the elements are same and this is a different pair because the other two is at a different index, you can consider that this would also follow the constraint. Okay. Now with this, the third I can see over here which can satisfy this particular condition is 2 and 3, I believe. So we do 2 and 3 once. Okay. So I'm considering these two elements, and then I'm doing 2 into 3. Again the modulo with 2. Okay, so here when I do this, right, 5 modulo 2 1, and this is 6 modulo 2 0 again, right? So with that I can say the elements at the index 2 comma 3, and with that, since if this is a valid pair, then this is also a valid pair, so element at the index 3 comma 4 is also going to satisfy this equation. Hence we have our 4 elements which are basically, or 4 pairs which are basically satisfying this particular Fermat's extra large theorem. So hence in the answer we have 4. Okay, remember you don't have to find out these pairs, right? This is just for your understanding to prove whether a pair satisfies or not. In the end we just need the count of all those pairs. Okay, so that's pretty much what the problem statement over here is. Okay, and that is how we got the output 4. Remember, you have to take in mind the constraints for the question. So the value of n, which is the size of the array, can never go above 10 to the power 5. The value of m, with which you are taking the modulo, can never go above 10 to the power 6, and s and p values will never be above m, because when you are obviously taking a value mod with m, the output is always in the range 0 to m, right? So it hence makes sense to always take the values of s and p in this particular range, and each and every element of the array a of I is always going to be either from 1 to 1000. Never a value is going to be above or more than that. Alright, so I hope that helps you understand the question, right? And the problem statement is clear, which is definitely one important part while solving questions. Now the next part over here is how do we figure out an approach to solve this question, and then we will implement the solution as well to be 100% sure that our approach is clear. So let's move to the next part. Alright. Now, so for solving this question, what we are going to do is, we are going to figure out an optimized way that will help us to give answer and identify all those pairs, right? Not exactly pairs, but the number of pairs which are basically satisfying the Fermat's extra large theorem. Okay. Now for that, what we are going to do is, we are going to make one very important observation, which was that if you see the input 1, 2, 3, 2, right? Here, the frequency of elements is very crucial, right? Why? Because if you remember, the moment we formed a pair of 1 and 2, right? It immediately led to the idea that this pair is also possible, correct? So that is why we could also form one pair, this 1 and 2, which was this, and another pair 1 and 2, which was this. So if you find two elements, right, which are basically satisfying the Fermat's extra large theorem, and if the other element, right, has a frequency greater than 1, we need to account for that frequency as well in our final answer. Okay, so what we are going to do for that is, first we are going to figure out the frequency for each and every element and store that in an auxiliary array. Let's say we call it the frequency array only. So here, if I consider the indexes 0, 1, 2, 3, 4 and so on, right, we can see that here it will contain 1 because the frequency of element 1 is 1. The frequency of element 2 is 2, so we're going to have a 2 here, and then for 3 we're going to have 1 and rest 0, 0 for the rest of the elements. Okay, so make sure you understand this idea very well over here. Okay, that first we will be storing the frequency for each and every element over here. Okay, now what we are going to do is we are going to iterate kind of over this frequency array itself. Okay, so first what we are going to do is, let's say I is basically a pointer which will run to the end of the array, and simultaneously for that we have an index j which will be like the second element for forming the pair. So it's like first we'll try to form a pair of 1 comma 2. Okay, then we'll try to form a pair of 1 comma 3, then we'll try to make a pair of 1 comma 4 and so on. Okay, so then we'll try to make a pair of 2 comma 3, then we'll try to make a pair of 2 comma 4. Okay, these are the elements. So indexes are nothing but the elements, right? 2 is nothing but an element which is having the frequency 2. So we're going to iteratively in two nested loops going to form all of these pairs. So it's like for I till the frequency dot length array, because we need to form each and every pair, and similarly the j index, right, which will start basically with I, right, and then will go till the end of the array again. Okay, because we have to form all the pairs. Now once we do that, we will basically just check the visibility of these pairs, so that if I plus j, right, and when I do the mod of it with m, if it is equal to s, and when I do I into j, again do a mod of m, and that is equal to p, right? So for each and every pair we are kind of checking that. First the pair is 1 comma 2, then the pair is 1 comma 3, then the pair is 1 comma 4, right? So on in two nested loops. We're trying to form all of the pairs, and for each and every pair we are basically checking if this condition, both of these conditions, that is why there is an and over here, both of these conditions are satisfied or not. Okay, so that's what we are checking over here. Once we know that this kind of a pair is particularly satisfying this condition, what we simply do is, in the final answer we just account for the frequency of both of these elements. Okay, so here, since let's say there is 1 with 1 frequency and there is 2 with 2 frequency, right, so basically the number of pairs possible is this, right, this and this, correct? So this is this pair and this is this pair. So total number of pairs is 1 comma 2. For example, if let's say there would have been the elements 2 and 3 which satisfied this condition, and 2 was present twice and 3 was present thrice, right? So the total number of pairs possible was 6, which was nothing but 2 into 3. Okay, just to take one other example, let's say there is an element 3 and there is, let's say, an element 5. Okay, 3 has the frequency 2 and 5 has the frequency, let's say, 4. Okay, that means in the array 3 is present twice and 5 is present 4 times. So these are like all the pairs that you can form, which is in total is 8. So whenever you realize that this condition is being formed, your final answer is nothing, like final answer is the frequency of all the counts, is nothing but the frequency of the element I multiplied by the frequency of element j, right? So that will help us to make sure that we account for each and every frequency and we don't have to do some recurrence or repetitive iterations over here. Remember that here we are not iterating over the original array. Okay, we are simply iterating over the frequency array, because here the frequency array indexes are basically defining the elements itself. So I and j over here are nothing but the indexes which represents the elements itself. So with this simple approach we would be able to find all the pairs, right? So I hope that helps you to understand how we are going to do this. Now I think we have a clear idea on how this is going to work. So we can simply move ahead and look at the implementation for this question. So let's move ahead. Now let's take a look at the implementation. So here you can see a basic stub code is already provided. This is nothing but a way how we can take the input from the terminal, and this is where in the main function we are going to write our actual code. Okay, so the actual code first involves taking the input for n, m, s and p. So that's what we're going to do. We are going to take 4 variables n, m, s and p. Okay, and then what we're going to do is we are going to take the input in an input array. Okay, so for taking an input from the terminal, a basic way how we can do it is we can do readline dot split dot so we can do the input of all the input given on terms of spaces. Okay, and then we are going to map each and every input like the converted array, and we are going to parse that input x. Okay, so that will give us the entire input over here. Next, the input array basically contains an array which has all the elements. So we are now going to divide it. So n is going to be input array of 0. Then we have n, then we have m, then we have s, and then we have p. Okay, and the indexes are 0, 1, 2, and 3. Okay, now once that is done, now we are going to take the input for the other array, which are nothing but the array elements. So let's call it input array 2. Okay, again the same way for taking the input from the terminal over here. Now this is basically containing an array with all the input elements. So here we are going to make a frequency array also, which is nothing but a new array of 1000 size, because if you remember, each and every element can at max be 1000. Okay, it cannot go above 0. So we are going to have an array of this size, and then all the elements initially have a frequency 0, and with that I will also introduce a variable which is going to have the final count, and at the end of every way we are going to, let's say, print the value over here. Okay, so first we'll fill the frequency array. So for that I am going to do this I less than 1001. This is the size of array, and less than we're going to do I plus plus. So we're going to take the input array elements, each and every element. Okay, and in the frequency array, the temp element now becomes the index, and we just increase the frequency, right? Pretty much what we wanted to do. Now we are going to start with the element at the very first index. One that is less than 1001, which is the length of the frequency array, and we're doing plus plus. Let's not take var because it's value. Let's do I. Okay, and then what we're going to do is we are going to have j now, which is starting at I. J is again less than 1001, and then we do j plus plus. Okay, remember an important I would say check here, which is frequency of I. If any point of time is 0, then we continue. No need to check the rest, because if the frequency of an element is 0, that means the element itself is not present. So now with this, we need to check two things over here, right? That I plus j, okay, when taken the mod with m is equal to s, and remember and, not or. I plus j when since I multiply by j mod m, it should be equal to p. Okay. Now, if this is true, okay, what we are going to do is, now here also now there are two things that needs to be taken care of, which we did not discuss earlier. Let's say there is this, okay, and the element 2 and 2, okay, both the elements, same elements, okay, basically form a pair and their frequency was high. So let's say here there was another 2 over here, okay, and the pair that is formed is of the element 2 and 2 only, okay. So it's like same two elements are basically satisfying the extra large Fermat theorem. So in that case, how do you satisfy the condition is that the final answer is going to be multiplied by the frequency of 2 multiplied by the frequency of 2 only, but doing a minus 1 to that, and then doing and taking the entire mod by 2, which means that the frequency of 2 was 3 multiplied by the frequency of 2 again but minus 1, which is 2, and then doing a mod of it by 2, okay, which basically means 6 by 2, which is 3, okay. So and that is correct also, because one pair that you formed was this of 2 and 2, right? One pair that you formed was this of this 2 and 2, and one pair you formed is this and this, correct? The first and the third 2, so 2 and 2. Apart from this, you cannot make any other pair which is different in terms of element indexes. Again repeating, this is one pair, this is one pair, and this is one pair, and the formula for that is going to be this. So we need to consider that over here. If I is equal to 80, okay, so in that case the answer is different. The answer is frequency of I multiplied by frequency of I minus 1 by 2. Okay, that I hope that helps. Otherwise, in the else case, what we do is simple as that, which is multiplying the frequency of both the elements. Frequency of I multiplied by frequency of j. Okay, and at the end of each and every time that you basically find out an answer, right, after each and every case where you have considered and find out the answer, you are simply just going to print the output. Okay, that looks good to me. Let's try to run this also. So I'll do node format.js. This will give us the active terminal. I will give it the input, and now you can see the output is 4. D is basically because I pressed Ctrl D to get the output, but here you can see the answer is 4, which we required as well. Just to reiterate on what we did, we just simply declared a variable. We took the input for the values of n, m, s, and p. This is a standard way of taking the input, okay? And this, you can read more about it on how we take input like these. And then here you can see that we took another input, which is for the next line, which is for the array elements. Then we just basically stored the frequency of the elements, right? And then we just simply took care of the frequency, and iteratively we tried to find out how many elements are there, which is basically satisfying that particular Fermat's extra large theorem. Okay, and in the end we're just finding out the answer. This was an important scenario where a 2 and a 2, both of the same elements, can find out be a pair, and in that case this is how we follow the formula, and which is hence proven here as well. In other cases, we just multiply the frequency of both the elements. Remember, if a particular element is having a frequency 0, we essentially do not consider it, and we just simply give the output and just move forward to the next element. Alright? So that should help you to understand how the overall idea works. I hope with this I was also able to help you understand the problem statement better over here, right, and how does it works. Alright? Okay then, I'll see you with the next question. Thank you so much.